Great. Well, good afternoon. My name is Scott Palo. I'm here to talk to you about some work we're doing on a low-cost transceiver for CubeSats. I also want to acknowledge my co-authors at the University of Colorado, Darren O'Connor, Elizabeth Alito, Rick Conert, and also my colleagues at the NASA Goddard Space Flight Center. So to get started, I wanted to kind of give you a big picture about what the project's about before we get into some of the details. And so overall, our goal here was to develop a CubeSat transceiver that's compatible with the NASA Near-Earth network. So the idea is to develop both an uplink capability and a downlink capability that we could be using for CubeSats to leverage the NASA Near-Earth network that currently exists. This was supported by a NASA call for cooperative agreements that came out in 2013. And one of the requirements for these agreements was that it had to be universities working with NASA centers. So not only was there a technology component to this program, but there was also the vision that there would be students and faculty involved working closely with technologists at the NASA centers to help infuse some technology into new directions. And so that's what funded this basic program. In terms of the team, this shows our structure. So I'm at the University of Colorado in the Aerospace Engineering Sciences Department and PI, and my colleagues are with the Laboratory for Atmospheric and Space Physics Lab in the, or LASP at the University of Colorado. Additionally, we have colleagues at Goddard, NASA Wallops and Greenbelt facilities, and also at the Marshall Space Flight Center. And last year we had a team of 5 undergraduates from the Electrical and Computer Engineering Department working on our S-band uplink as part of their capstone project for their coursework. Before I get into the details of the project, I just wanted to give you a little bit of background for those who may not be familiar with the Laboratory for Atmospheric and Space Physics at the University of Colorado. It was founded in 1948, 10 years before NASA, doing sounding rocket work. Since that time, LASP has sent instruments to all 8 planets plus Pluto, or there's an instrument on the way to Pluto now on the New Horizons mission. And LASP combines both space exploration and science and engineering, mission operations and scientific data analysis, and we work together with students and engineers to train the next generation of engineers and also to attack compelling science and engineering problems. And you can see the picture in the middle there is a picture of our Minx CubeSat, which is going to be delivered in January. It's our second CubeSat. The Colorado Student Space Weather Experiment's been on orbit now for 2 years. That's a team of students that worked on that project, and that has a miniature X-ray spectrometer that will be on board to look at the sun and the extreme ultraviolet. So why do we want to go to X-band? I think a lot of people here are familiar with the challenges we have with getting data down from small satellites. On our current CubeSat, the Colorado Student Space Weather Experiment, we're operating in the 70 centimeter band at 437 megahertz at 9,600 bits per second. And we've collected over 160 megabytes of data from that mission to date. However, when we scoped that mission, one of the key things we took into account were, in fact, 2 factors. One, we had passive magnetic attitude control, so we did a mission that could do science with passive magnetic attitude control. And 2, we only had about 10 kilobits of downlink at a single ground station, so we needed a mission that would fit into that box. So the mission that we flew for our first CubeSat was actually measurements, where we were counting particles in a number of energy bins every 6 seconds, and so that was data that we could fit into the requirements we had for our mission. If we look at X-band, and our interest is to go up to greater than 10 megabits per second, you see that's over 1,000-time increase in the data rate that we can get down. So in fact, the 2 years of CSSWE data could be downloaded in 3.4 minutes at a 12.5 megabit per second video. So in a single pass, we could get all the data. It's taken us 2 years to get down on the current CubeSat mission. So that gives you an idea of scope. I also think that jumping to X-band and the higher rates will also enable a lot of new types of science missions, particularly when we start looking at imaging and the Earth observing network. So one of the big challenges, as I learned in getting into this project, let me back up a little bit. One of the reasons why I was interested in doing this project, I was interested in learning about building a radio, and so the technology aspects of it. And one of the things you find out pretty quickly, and one of the big challenges isn't the technology, but actually the frequency coordination. So you can see this is the US spectrum. The spectrum is quite crowded, as we're all aware, but if you zoom in, There's a second section of spectrum here in the orange, which is the Earth Space Satellite, if I can read it here, the Earth Explorer Satellite Network. So there's a service there from about 8025 megahertz up to 8400 megahertz in the X-band. That's where the NASA Near-Earth Downlink operates at, and so that's the band we're targeting. Something else I should make you aware of for anybody that's interested in doing this type of work, starting at 8400 megahertz is the Deep Space Network, and they are very restrictive about any spectral leakage into their band. So you also have to be concerned when you're building radios in this band to make sure you're not leaking over into the Deep Space Network. So we've been taking that into account. So what are we looking at for our project here? The idea, as I mentioned previously, was to develop a radio that's compatible with the Near-Earth Network, 200 kilobit per second S-band uplink, and a 12.5 megabit per second X-band downlink. Initially, we wanted an architecture that would be scalable to over 100 megabits per second. So the approach we're taking is scalable. Obviously, it takes more power, but the idea is that NASA was also interested in using this on their sounding rocket program on Palo. Our approach is to use commercial off-the-shelf parts, so we're not using any radiation-hardened parts. We're buying things off the shelf. The idea was also to minimize complexity and make this as bare bones as possible to get it functional and push the complexity to the software where possible. We've used RF software design tools to actually do the design, because when you start looking at doing the RF work, the amount of time it takes to iterate and build hardware is time consuming, so we wanted to push as much of that into software design tools as possible, and in that process we learned which tools were robust to what we were trying to approach. And we were going with a build, test, and iterate approach to try to get hardware out in about a 3 to 4 month cycle, learn from that, and then do a second revision. Our schedule for the first year was to mature the technology on the X-band transmitter downlink, and that's what I'll be talking about, taking it from a TRL3 to TRL5, which means being tested in a relevant environment. So our target, and this program's target, was to move technology from low TRL of 3 to 4 up to a TRL of 5 or 6. And in year 2, which we've just begun, is to work on maturing the S-band uplink aspects of the project. As I mentioned, we want to be compatible with the NASA Near-Earth Network, and so this is a picture of the wall. So 11.2 meter dish. At X-band, it runs from 8,000 to 8,500 megahertz. It has a system noise temperature of 170 Kelvin and has a gain of about 57 dBi. So you can see that it's a fairly large dish, and that helps when we're trying to talk with CubeSats that have a large collecting aperture on the ground. Now, well, I'll get to the system piece in a moment here. That doesn't mean you can't use a smaller antenna on the ground. It just means that if you were to do that, you'd have to reduce the data rate, and the architecture is scalable to lower data rates. So to give a little bit of perspective and talk a little bit about where the system design aspects are coming from, I wanted to show you a link budget here, and this is looking at how do we get data from the satellite down to the ground, and the things we need to think about, and what are the components on the bus, and what are the components on the ground. So wanted to start talking over about the space segment on the left, and the key element that you're interested in there is what is your effective isotropic radiated power. Essentially, what's the power per unit area that you radiate away from the spacecraft. And that's a combination of your transmit power, the gain of your transmit antenna, and your system losses. From the communications channel in the middle, there you have the spreading loss due to the range to the spacecraft. And additionally, you have atmospheric losses and polarization losses. If we're looking at a satellite at about 700 kilometers and at an elevation about 5 degrees above the ground, that puts it at a range of about 2,500 kilometers, which gives us a loss of about 181 dB. And then if we look at the ground segment over on the right, we can look at how much power do we need to, or what's the power that we receive, and that's equal to the power we radiate, subtracted from the propagation losses, plus the gain of the antenna on the receive side. And we can also calculate what the noise of our ground station is, which is a function of both Boltzmann's constant, the actual temperature of the receiving system, and the bandwidth of our system. So as we go to a larger bandwidth, the received noise goes up, and that drives your signal noise ratio down, therefore meaning you either need more transmit power or a larger antenna. So we can calculate the required signal noise ratio as simply the difference between the receive power and the noise power. And if we go now and look at the question is, what is the required signal noise ratio to close our link? Well, that depends on three things. It depends on what is the bit error rate you're trying to achieve, what is the modulation scheme you're using, and then what type of forward error correction coding you're using. So there's a family of curves over on the right that shows the nominal bit error rate versus signal noise ratio for a range of different modulation schemes. We've chosen to use offset quadrature phase shift keying, and to achieve a 1 to minus 7 bit error rate with some forward error correction convolutional coding, we need a signal noise ratio of about 5.5 dB. If we then go back onto the previous slide and assume a 170K receiver on the ground, operating at 12.5 megabits per second, it gives us a receive power of about minus 130 dB watts. And if you look at the difference between the required receive power and back out what is the required power that needs to come out of the spacecraft, we need to have an effective isotropic radiated power of about negative 6.5 dB to be able to close the link at 12.5 megabits per second from space to a ground station in the near network. So if I go back and look at what are the two things I have to trade off there, I can basically trade off my antenna gain and I can trade off my transmit power. If I assume that I have a 1 watt transmitter and an omnidirectional antenna, so no antenna gain, I have about a 6 dB link margin. So what that says is that I can even drop my power down to about half a watt and still have 3 dB of link margin, or otherwise I could make a smaller dish on the ground and still close the link, or if I reduce my data rate by a factor of 2, then I can even go to a smaller antenna. So there's pieces you can trade off here, but again, what we're looking at is closing the link from LEO to the near Earth network, which says that transmitting about half a watt to a watt is sufficient to be able to close that link at 12.5 megabits per second all the way down to 5 degrees above the horizon. So here's a block diagram of our approach to implementing our design. So if you look on the left, I don't know if I have a mouse, so I'll just point it out. Over on the left here, we have our data coming in. So data coming in at 12.5 megabits per second, and our clock coming in at 25 megahertz. That comes into the FPGA, which then does the forward error correction coding and outputs the in-phase and quadrature data streams coming out to the right, which come out as digital signals and then get filtered. So that's where we do our filtering to limit the output bandwidth of the signal. And then we go in through a vector modulator, and that vector modulator does a direct convert from baseband up to X-band. And the nice thing about going with a single vector modulator rather than doing a heterodyne approach with multiple stages is we have less spurious signals we're generating, and there's less intermodulation harmonics that get generated, which then go into out-of-band spurious signals that you have to worry about. So we come out of the vector modulator, we go into a two-stage amplifier and then out to the antenna. And then also, you can see we have a voltage-controlled oscillator, and so this is scalable as a function of programming the oscillator to different frequencies. And I should also point out that the output data rate is scalable by the input clock. So if you want to run the radio at a slower rate, you run the clock on the data rate slower. So this is just to show that we have an approach and a theoretical approach to doing the simulation, so we can actually simulate different modulation schemes and different channel characteristics and simulate and compare this with the output and have good results. Here's a picture of what the hardware looks like. This is Rev 1. You can see the size is a little bit smaller than 10 centimeters by 10 centimeters. There's a number of test connectors on here that'll disappear, and we believe we can reduce that board size by probably another 20%. And this board has been built and functionally tested and shown to operate at ambient, and we're going to be putting it into the thermal vac chamber here at the end of this month so that we can reach TRL5. This shows the output spectrum operating at 12.5 megabits per second, and it just shows that we meet the NASA Space Coordination Group mask for output emissions, so we're within the output requirements. I won't talk about this. I'll show here that you can see we also don't generate spurious harmonics. You can see our fundamental down here at about 8200 megahertz, and then you can see the first harmonic out there at 16 megahertz, which then gets filtered out by a stub filter that we we have implemented. And then the results, we've also compared the output bit error rate calculated from our system to theory that we expected. So we had this tested at Goddard Flight Facility, and they tested it with their receiver and characterized the bit error rate. We can see that we're within about a dB of what we expect to be getting. So just to wrap up here, I wanted to say that we have verified functional performance of the X-band transmitter. TRL verification will occur at the end of this month. We'll be doing TVAC testing at LASP and then bit error rate testing at Goddard. We have funding from Goddard for an internal research and development project to fly this on a balloon or a rocket in the second quarter of 2015 and move it further up the TRL. And we're looking at also a potential flight opportunity later in 2015 and 16. And we'll be doing ground system testing with a partner and later this year to look at compatibility, and we're looking doing some initial discussions about commercialization of the system to make it available to the community. So that's all I have. Thank you.
Thank you very much. Are there questions? No questions? Okay, there is one.
How large will your antenna be for such a transmission? Or maybe I missed something.
So right now, with the current analysis, you can use a simple X-band patch antenna. I haven't done the design on that, but you can look at the size. You can look at an S-band patch antenna, which is a few centimeters on a side, and X-band is going to be probably about a factor of 4 smaller than that. And I know that JPL is looking at designing an array that will give better than 10 dB directivity, so that you could actually if you have pointing capabilities, could increase the throughput of the radio by having more gain on the antenna.
One more question?
What are the, do you have any idea what the attitude requirements are for an X-band?
So if you use an omnidirectional antenna and you use a splitter, you can take 2 omnidirectional antennas and put them on both sides of your spacecraft and cover all 4 pi steradians. And so in that case, there is no attitude requirement. Even if you go with a directional, let's say 10 dB type antenna, those those beam widths are going to be on the order of 30 degrees. So you don't have real stringent pointing until you get to antennas that are going to be, let's say, 20 dB of gain.
Is there a final question? No question anymore? Thank you very much.
Thank you.